Chapter 6, problem set 4. Chapter 6, problem set 4. First one is question 11, not problem 11, question 11. It says a person riding a Ferris wheel moves through positions at the top, position number 1, at the bottom, position number 2, and at the mid-height, position number 3. If the wheel rotates at a constant speed, rank these according to the magnitude of the person's centripetal acceleration. So the first thing we're looking for is centripetal acceleration. Then the magnitude of the net centripetal force on the person. So we need the net centripetal force and the magnitude of the normal force. So F normal, okay? Well, I think that to start, we should draw some force diagrams for these. So let's draw the force diagram for the guy at the top. So if I look at the force diagram for the guy at the top, well, I know he's got some weight there. That looks pretty good. Okay, we'll call that one mg. In fact, what's interesting about this is, regardless of where they are, they all have the same mg. Like, your weight doesn't change. Okay? So, but we know he's in circular motion, therefore, the net unbalanced force needs to point toward the center. So what does that mean? Well, that means for this guy down here, the normal force must be greater than the weight because the net unbalanced force needs to point toward the center. What does that mean for this guy here? That means that his normal force must be less than the weight because the unbalanced net force has to be toward the center. And what about this guy here? Well, interestingly enough, for this guy, there has to be a force inward because there has to be a net unbalanced force toward the center. So here the normal force is equal to the weight. Here the normal force is less than the weight. Here the normal force is greater. That doesn't even answer the question. So the first question is, how does the centripetal force compare? And the answer to that one is, well, centripetal force is equal to mv squared. Nope, just kidding. Centripetal force is equal to v squared over r. And since they all have the same speed and they all have the same radius, the answer is all the same. Centripetal force is mass times centripetal acceleration, which is equal to mv squared over r, but they all have the same mass, same speed, same radius, so therefore, all the same. And what about the normal forces? Well, as we saw here, the normal force at 1, then 2, then 3, so the largest is 2, then 3, then 1. Cool. All right, let's move on to problem 47. I think it's another Ferris wheel problem. It says a circular motion addict of 80 kilograms, let's write that down, mass is equal to 80 kilograms. Rides a Ferris wheel in a vertical circle of radius 10 meters. Ooh, that's going to be important. meters at a constant speed. All right, so it says here that the speed is equal to 6.1 meters per second. What is the period of the motion? All right, so if you're going around in a circle, we know that speed is equal to the distance divided by the time. Now, if you're going around a circle, this is the circumference. And if you keep going around and around and around, the time it takes to go around once is called the period. So speed is equal to 2 pi r over t, where capital T is the period. So if I want to solve for that, I'm going to do 2 pi r over v. The radius is 10, and the speed is 6.1. So it's going to take him 10.3 seconds to go around once. Okay? So now they want to know what is the normal force at its highest point and the normal force at its lowest point. Well, in the last problem, if you were paying attention, you saw some force diagrams here. So the force diagram for when it's at its highest point, you have the weight mg, and the normal force here is less than the weight because the unbalanced force has to be down. So I know the net force is going to be equal to mass times acceleration, but it's centripetal, so it's mv squared over r. The net force in this case is going to be equal to mg minus n, because I like to do big minus small and keep my values positive. So I end up with mv squared over r is equal to mg minus n. And now I think I can just plug and chug this. So I end up with 80 kilograms times 6.1 squared, all divided by 10, is equal to mg, which is going to be 600, minus the normal force. So I got N is equal to 302 newtons. Now, what about the bottom? Well, we saw the bottom earlier. We know the normal force has to be bigger than the weight because the unbalanced force has to be up. So, centripetal acceleration, mv squared over r. This time, though, the net force is going to be equal to normal minus the weight, because I like to do big minus small. So I have 80 times 6.1 squared divided by 10 is equal to normal minus 600. There you go, 898. $49 says, in this figure, cars driven at a constant speed over a circular hill into a circular valley with the same radius. So in this, although my drawing is a little sketchy here. Oh, that's funny, not upon this radius here. We want to equal this radius here. Okay, keep that in mind. At the top of the hill, the normal force on the driver is 0. Yikes. Probably going to be important. It says the mass of the driver is equal to 70 kilograms. What is the magnitude of the normal force on the driver from the seat when it passes through the bottom of the valley? All right, I like this. So if I draw this, okay, I'm going to put the car here. Changing the color a little bit. All right, if I draw this here, and I draw a force diagram for this, and then I'll put it in down here. So same car, same driver, same speed. Let's draw a force diagram for this one. Okay, well I know he has weight. He's got mass, he's in the gravitational field, we'll call that mg. This one over here, same thing, 1, 4. But consider this for a moment. The unbalanced force needs to point toward the center. So here, the center is up, which means that this normal force has to be 1, 2, 3, 4. okay? The normal force has to be a lot greater than the weight. And this is what we're going to solve for eventually. Here, normally, we would put a normal force on here, right? Except for the fact that it says he's going fast enough that the normal force is 0. Now, what that would mean was actually that you were out of your seat. You went fast enough as you came over the hill that you left your seat a little bit. That, to me, is really interesting. So it says that the speed is constant for both. We need to solve for the normal force. Okay, so let's start over here. I know that when I look at the net force, it's equal to mass times acceleration, but it's centripetal, so it's mv squared over r. Here, when you look at the net force, well, the normal force is 0, so it's just equal to mg. Therefore, mv squared over r is equal to mg. Now, we could do some substitution here, but we're going to pause on it and see what happens. So over here, when I look at it, I notice that the net force is equal to mv squared over r again, because we have the same circular situation. This time, the net force is equal to n minus mg. So if I set these equal to each other, now I want to solve for the normal force. Here's the cool part. Don't I have an expression for mv squared over r over here? Isn't it equal to mg? So I'm going to make that substitution. So it's equal to mg plus this mv squared over r, which is mg, so the normal force is equal to 2mg. So in this case, it's 70 kilograms, so n is equal to 2 times 70 times 10. And because his normal force is twice his weight, he feels twice as heavy. All right, I think there's one more. 53. So this is a back view here. Okay, so 53 says, an old streetcar rounds a flat corner of radius. It's a flat corner. It's going to be important. It's a flat corner. All right. And it says the radius is equal to 9.1 meters. Okay, and it says at 16 kilometers per hour. That's annoying. So speed is equal to 16 kilometers per hour. Let's figure out what that is in meters per second. Okay, 4.4. Cool. Now, what it asks here is, what angle with the vertical will be made by a loosely hanging strap? So I drew this strap here, it's loosely hanging. So if you round this corner, it's going to slide out a little bit, and we want to know what angle is made here. Is that cool? All right, so you can use the strap or the center strap or the end of the strap. I'm just going to draw a quick force diagram for it. Okay, let's pretend there's a ball on the bottom. It'll be easier to draw the force diagram. So we know that here's the strap. The earth is pulling it down. We call that mg. Now, the string is pulling, or the ceiling is pulling the string, or the string is pulling this way. The same context is fine. All right, and we're going to call that the tension. And we know that if it's rounding a turn, what do we know? We know the acceleration is inward toward the center. So as long as the acceleration is inward toward the center, what it's going to tell me is that there's no vertical acceleration. So here's your angle here. Now, if I look, you see this dotted line here? It would be the same as up here. True? All right, so F net in the y direction. Well, if we call this t, we're going to call this t in the y direction. Call this one t in the x direction. F net is equal to ty minus mg. But there's no acceleration in that direction. So F net in the y direction is equal to 0. Therefore, the t in the y direction is equal to mg. All right, what about the F net in the x direction? Well, there's only one force in the x direction. That's this thing here, that's the tx. So it's just tx. But it is accelerating in the x direction, which is centripetal mv squared over r, because it's taking a circular turn. So therefore, the t in the x direction is equal to mv squared over r. Now, we go back and we look at my angle here. What side is opposite? It's the tx. What side is adjacent? It's the ty. So I can write a tangent statement. Tangent is equal to tx over ty. But I have statements for each of those, like the tx is mv squared over r, and the ty is mg. The m's magically disappear, and you're left with v squared over rg. And so if you want to find the angle, okay, let me plug this in. $12 degrees.